In this video, we're going to look at an alternative way of trying to rule out a stationary point as a maximum and a minimum, and then concluding it's probably got to be a saddle point. So for a point to be a maximum, it must be a maximum on all sections that go through the point. Again, and similar applies for minimums. It must be a minimum on all sections that go through the point. Now, what do I mean by that? Well, I'm going to demonstrate it using point A, our maximum, okay, which is this point here. So let's now consider a section at A. So let's keep the x coordinate the same, okay, and only change our y coordinate. So if we get the x coordinate at what appears to be maybe roughly 0 and just move the y coordinate, we'd end up with the following, like that. Now you can see on the bit of the graph in blue that I've drawn, that red point is indeed a maximum on that bit of the graph. Okay, so it's a maximum on that section, so that seems to check out. Now let's do the alternative, okay, and let's keep the y coordinate the same. So that's going to be roughly, I think, 0 again. Okay, but let's change the x coordinate. Okay, and the bit of graph we would get would be the following. So we get down there, and then it would go like that. Okay, and on that orange bit of the graph, you can see the point A is a maximum on it. Okay, that should be the case for any section that you make use of. Okay, we can't consider every single section that goes through a point. Therefore, we cannot use this to conclude something's a maximum or something's a minimum. However, what we can do is rule out maximums and minimums. Okay, so if we look at point D, which is our saddle point, as discussed previously. Now, let's say we took the section in this direction here. Okay, you can see on the new blue bit I've drawn, okay, that is a minimum. D is a minimum on that. So let's now consider another section. Okay, so if I start from drawing down here, now apologies for my drawing as we go into this next part. Once it gets to D, it's been increasing up until there. It's then going to dip down into the gap down there. Okay, so D is going to end up being a maximum on this section. So there's a maximum on one section, a minimum on another. So therefore, D can neither be a maximum or a minimum point on the whole surface. Instead, it would have to probably be a saddle point. So let's go through an example of using this. So we've got the same surface as last time and the same stationary point. Okay, what we're going to now do is go through and use sections to help determine that this is neither a maximum nor minimum. So the first section I'm going to consider is when x is equal to 4. Okay, so section when x is equal to 4, which is the x coordinate of our stationary point. Okay, so we know that this section is going to go through that point there. So what I'm going to do is substitute x equals 4 into our surface equation, so we get the equation of the section. So I'd have z is equal to, and it would be 4 squared, take away 4 times y, take y squared plus 20y, subtract 15. Now if I simplify what's written there, we're going to get 16, take 16y, take y squared plus 20y, subtract 15. And then simplifying further, we'll get negative x squared, and then positive 4y, and then positive 1. Okay, so we've got the equation of my section. Now what we have to investigate is at my section, when the y coordinate is specifically equal to 2, okay, is that a maximum point or is that a minimum point? So in order to do this, we're going to use the second derivative, okay, which you should have learned in your single maths lessons. So we're first going to have to differentiate. So this is z is equal to negative y squared plus 4y plus 1. If we differentiate with respect to y, we would get negative 2y plus 4. Okay. We're not going to substitute our y coordinate into there, because if we sub it into there, we're going to get 0, because we know when y is 2, it should be a stationary point. Okay, we're going to go one further and differentiate again. And then we're going to substitute our y value into our second derivative. So our second derivative comes out as negative 2. And because it's independent of y, we don't actually have to substitute a value of 2 in ourselves. Okay, what we've established is the second derivative is always smaller than 0, regardless of the y coordinate. Okay, so therefore, the point 25 is a maximum on this section. Okay, and I've got the 5, that's the z coordinate that I know is going to be on that section. Okay, so we've established on this section we have a maximum. So now what we have to do is repeat the process I've just done. Okay, but instead of doing the section when x equals 4, we're going to do the section when y is equal to 2. So we're going to substitute y equals 2 into our surface equation. So I'd get z is equal to x squared, take 4 times x times 2, take 2 squared plus 20 times 2, subtract 15. And then we're going to simplify it. So I get x squared, take 8x, take 4, plus 40, subtract 15. And then collecting our like terms, and we would get x squared, take 8x, and then positive 36, positive 21. So this is the equation of my section. We're now going to investigate whether it's a maximum or a minimum. So to do that, we're going to have to look at the second derivative. So we're going to first find our first derivative, which would be 2x subtract 8. Now, if I was to substitute the y equals 2 into here, you would get 0 because it's meant to be a stationary point, but we want to classify the stationary point. So we're going to have to go to the second derivative, which comes out as 2. Now, if this had come out with x in it, we'd then have to substitute x equals 4 into there because that's the x coordinate of the stationary point. However, because it's just come out as 2 independent of x, we can already make our conclusion. Okay, it's always going to be greater than 0 regardless of what x we use. Okay, so therefore, the point 4, which is our x coordinate, comma our z coordinate, which is 5, is a minimum on this section. So it's a maximum on one section, a minimum on another. So therefore, it can't be a maximum or a minimum on all surface. It's going to have to be probably a saddle point. So we can make one final conclusion. We can say, therefore, it's a minimum on one section through 4 to 5, but a maximum on another. So 4 to 5 cannot be a maximum or minimum on the surface.